Hi friends, welcome back to Edupedia World. The last lecture we discussed about the concepts of a liver, and today's lecture will be exclusively on certain examples of liver. So let us straight away jump and see the examples. The question says that we have a crowbar which is of length 1.5 meter and it is pivoted at 30 centimeter from the end of load. So from this statement, let us try to draw what the crowbar will look like. The total length, it says, is 1.5 meter and it is pivoted at 30 centimeter from the end of load. So if here we keep the load, then somewhere here will be the pivot, and this will be 30 centimeter, and the total length we already know is 1.5 meter. From this we can say that since the fulcrum is here, the load will be here, and obviously the effort needs to be applied somewhere here, the fulcrum being at the center. This is a first class of lever. So that answers the first part of the question, what kind of lever it is, what class. So it falls into the first class of lever. Now second part states that find its mechanical advantage. We have just seen in the previous lecture, that mechanical advantage for a lever is effort arm upon the load arm. This is the definition of mechanical advantage. Now for the case at hand, what is the effort arm? The effort arm will be the distance between the effort and the fulcrum. Now the effort will be applied at this end. Let's try to mark it here, something like this, effort, and the load will be somewhere here, something like this, load. So the effort arm will be this particular distance, the distance between the fulcrum and the effort. Now the total length is 1.5 meter. This length is 30 centimeter. So this length will be 1.5 meter minus 30 centimeter or 0.3 meter, which will be equal to 1.2 meter. So it will turn out to be effort arm as 1.2 meter. Now we need to know the load arm. What will the load arm be? The load arm by definition is the distance between the fulcrum and the load, and the question clearly states that as 30 centimeter, but here we have written the effort arm in terms of meter, so we convert 30 centimeter into meter. That turns out to be 0.3 meter. Now 1.2 upon 0.3, that is 4. So the mechanical advantage for the crowbar is 4. Now the third part asks us to find the maximum load that can be moved by the force of 50 Newton. So what is this 50 Newton? This is the effort that is applied. So for the third part, what we know is that the effort is 50 Newton. We know that the effort arm is 1.2 meter. We know that the load arm is 0.3 meter. By the principle of lever under condition of equilibrium, we learned that load into load arm is equal to effort into effort arm. One important thing to understand is that this is valid for a perfect machine. That is, there is no losses, no frictional loss, no nothing. So load into load arm is equal to effort into effort arm. I missed it out during the lecture, but the fact is that this is valid when everything is perfect frictionless. There is no loss of energy. Now the question asks us to find the maximum load. So we'll take the condition, and the question does not mention any loss of efficiency. So we'll take 100% efficiency, and we will find the maximum load. So we need to find this. L into load arm is 0.3 is equal to effort is 50, effort arm is 1.2. This implies that the load is 50 into 1.3 upon 1.2 upon 0.3, which is 200. It turns out to be 200 Newton. So the maximum load that can be moved by a 50 Newton effort is 200 Newton. We did this part by using the relation load into load arm is equal to effort into effort arm, but we might have done it in an alternate way. How come? We know that the mechanical advantage is load upon effort. So since we are assuming an ideal system with no losses, we can directly use this. We can replace mechanical advantage as 4, as we already calculated in this part. The load is to be found L, and the effort is 50. This translates into load is equal to 200 Newton. So depending on the convenience, whichever method suits you better, you can either use this method or this method. The first method which I showed is more of a first principle method. That is, we are using the basic definition or the basic principle here. But the second method actually uses the formula derived by using this first principle. But both are equally valid. Next, let us see another question to understand the concepts and grasp the concepts much more clearer. This question gives us a diagram in which the fulcrum is at this end. We have a 10 Newton load here, and the effort is applied over here. The question asks us to find what class of lever it is. Now if you notice, then you see that the load is at the center. Now if you remember the theory, or if you go and look back in your previous lecture, you will see that when the load is at the center, the class of lever is second class of lever. So here the load being at the center, this is second class of lever. So that answers our first part. The second part says find the minimum effort to maintain equilibrium. What all do we have in the question given to us? We have the load, and that is 10 Newton. We have the load arm, that is the distance between the load and the fulcrum, as 4 meter. we have the effort arm, the distance between the effort and the fulcrum, as 4 plus 2, that is 6 meter. We need to find the effort. We know that load into load arm is effort into effort arm. So if we use that expression, load times load arm is equal to effort times effort arm, we know everything but effort. So effort will be load into load arm upon effort arm. Load is 10 Newton. Load arm is 4 meter. This distance upon effort arm. Effort arm is the whole distance from the fulcrum to the effort, that is 6 meter. That will be 20 upon 3, that is 20 upon 3 Newton, that is the effort required. And if we simplify it further, it will be 6.67 Newton. So the minimum effort required to maintain equilibrium is 6.67 Newton. What we see is that the effort was 10 Newton, but only 6.67 Newton is required to balance it out, which means that this is an example of force multiplier, or the effort is multiplied, effort multiplier. It's normally called as force multiplier. In the lecture I have mentioned it as effort multiplier too, but try to mention it as force multiplier. That is a more general term. So the second class of lever, as we have seen in the lecture, is a force multiplier, and here we see how it is through this numerical. Now the third part is, what is the mechanical advantage? The mechanical advantage is effort arm upon load arm, which will be effort arm is 6 meter and load arm is 4 meter. So mechanical advantage is 1.5. And as we discussed, this is compatible with the fact that a force multiplier has a mechanical advantage more than one. Now the last part asks us to find what should be the position of this load. Where should this 10 Newton be moved so that effort of 5 Newton is sufficient to maintain the equilibrium. So what the question asks is that we need to move this load, but where does the load need to be moved to? Now let me draw the diagram here. The fulcrum and the effort remains at the two ends. The load comes up somewhere here. It remains 10 Newton. The effort is mentioned in the question as 5 Newton. Now where should the load be? Let me take this distance as x. This is the load arm, and this distance then will be 6 minus x. Why? Because the total length remains 6 meter. The bar is not changed. It remains 6 meter. Only the location of the load is shifted in either direction. We don't know as of now. So we have taken that distance as x, and then this is 6 minus x. We have the load as 10 Newton. We have the effort as 5 Newton. We will go back and use the same relation, that is load into load arm is effort into effort arm, and let us see what that gives us. So the load is 10 Newton. The load arm is this between fulcrum and load, that is x meter. Remember, this is meter and 6 minus x is also meter. Is 10 times x is effort into effort arm. Effort is 5 Newton and effort arm is the distance between the fulcrum and the effort. So it is going to be the whole length of the rod, and that is 6 meters. This will give us x is equal to 5 times 6 upon 10, which is 3 meter. So x turns out to be 3 meter, which means that the load should be shifted 1 meter towards the fulcrum. So this new location will be somewhere over here. This is 1 meter. So this will be 3 meter and this will be 3 meter. So the load ultimately lands up at the center of the bar. And obviously so it should be at the center. Why? Because the effort here is half of the load. So obviously the effort arm should be double the load arm. And we clearly see that happening here. The previous example was an example of the first class of lever. This example was an example of second class of lever. Now let us conclude the exercise lecture with another question, which will be based on the third class of lever. This last question for this lecture today shows a bar which has the fulcrum here, the effort here, and the load of 100 Newton at the other end. So what class of lever is this? From the lecture we know that the third class of lever has the effort at the center. Since here the effort is at the center, this is a third class of lever. This is third class lever. The second part asks us to find the mechanical advantage. We know that the mechanical advantage is the effort arm upon the load arm. Here the effort arm is the distance between the effort and the fulcrum, and that is 2 meter as marked here. So we can say effort arm is 2 meter. Load arm is the distance between the load, that is the 100 Newton, and the fulcrum over here. That will be this whole distance, that is the length of the bar, and that will be 2 meter plus 3 meter. So it is 2 plus 3 meter, that is 2 upon 5, which is 0.4. So the mechanical advantage for the diagram at hand, for the lever at hand, is 0.4. What does this mean physically? Physically it means that the load will move at a more speed than the effort, since mechanical advantage less than 1 refers to a gain in velocity. So it is a speed multiplier. The speed of the load is more than the speed of the effort. In other words, it is required to apply a more larger effort. It is required to apply a larger effort to move a particular load. What I mean is that to move this load, or to balance out this load of 100 Newton, the effort required will be more than 100 Newton. That is what I can say just by saying the value of mechanical advantage being less than 1. Now let us check out if my prediction is right, because we need to find the effort required as a third part of the question. We will do it by the first principle way, that is load times load arm is effort times effort arm. Load is 100 Newton. Load arm is the total distance, that is 5 meter. Effort is unknown E, and effort arm is 2 meter. Effort and fulcrum distance 2 meter. This will give me effort as 100 times 5 upon 2, and that is 250 Newton. And we clearly see that the effort is quite large compared to the load, as was predicted just by saying the mechanical advantage. We have an alternate way of finding out the effort by using the definition of mechanical advantage. What is that? That is, mechanical advantage is load upon effort. If we use this, we will get 0.4 is equal to 100 upon E. If we simplify this, we get E is equal to 100 upon 0.4, which will give us the same answer as 250 Newton. So either this of this method can be used, and since this is the relation, it was obvious that value of 0.4 mechanical advantage hinted that the effort required has to be larger than the load. These three questions which we did in today's lecture gave a glimpse into all the three classes of lever, and we can handle questions of lever much better, much more efficiently. We have the concepts, a much better grasp on the concepts after this lecture. I suggest you to carry out some questions on your own, do some numericals to see if something confuses you still. Okay, that's it for lever. In the next lecture, we'll see inclined planes as a different type of machine. Till then, have a great day. Goodbye.